Hello and welcome to the Peace Talk. Welcome to another episode, and this time with Professor John Ellis. My name is Josef Mühlbauer. I'm an author, publisher of several books, scientific researcher at Empowerment for Peace, and a PhD student in political science. And today I have the great honor and privilege to introduce to you John Ellis. John Ellis is a professor of theoretical physics at King's College in London. His research interests focuses on the phenomenological aspects of elementary particle physics, astrophysics, cosmology, and quantum gravity. He has authored nearly 1,000 scientific papers, some with over 50,000 citations. He is one of the most cited theoretical physicists in the world, and he did also research on the Higgs-like particle discovered at CERN. I will not mention all his awards and prizes, but some of them are: he was awarded the James Clerk Maxwell Medal and Prize in 1982, the Paul Dirac Medal and Prize in 2005 by the Institute of Physics. He was elected Fellow of the Royal Society in London in 1985 and of the Institutes of Physics in 1991. He is also an honorary fellow of the King's College Cambridge, the Serbian Physical Society. He has been awarded honorary doctorates by the University of Southampton, Uppsala, Sofia University, and many more. He won twice the award in Gravity Research Foundation Essay Competition, and he was also appointed Commander of the Order of the British Empire in the Queen's Birthday Honor in 2012 for his services to science and technology. So with this, thank you, John, for that you followed my invitation for this Peace Talk.
Well, thank you very much for the invitation. Looking forward to it.
So let us begin with your discoveries and with theoretical physics. I'm not sure I'm able to talk about that, but I can listen. So how do you see discoveries in theoretical physics, such as, for example, the Higgs boson and many others? How can they contribute in, for example, addressing broader societal challenges, including, fostering global collaboration and many more?
Yeah, well, as a particle physicist, I'm primarily interested in trying to understand how the universe works at the sort of most fundamental level. What are the equations which determine, how the universe got started, what's it doing now, what's going to happen to it in the future. So, in a general way, I think that advances in this area I heard myself then. Shall I continue? Yeah. So I think in a general way, the better we understand the rules governing the universe, then that sort of knowledge, I think, is good. And it's interesting intellectually, but it may also have applications. And sometimes those applications are completely unexpected. Let me just mention just one example. So 100 years ago, almost, Dirac suggested the existence of antimatter when you try to combine quantum mechanics with relativity. Particles which had the same mass as, for example, the electron, but would have opposite electric charge. And the antiparticle of the electron, called the positron, was discovered a few years later. But I think everybody thought it was kind of a curiosity. But actually, it turns out to have applications in medical diagnosis. And thousands of people each year are helped by something called positron emission tomography, where they're injected with an isotope which produces positrons, which then annihilate with electrons, and you can, in that way, figure out the way that the metabolism works, for example, inside the human brain, without damaging it. So that's just one example of something which was completely unexpected. Another example, if you like, is general relativity, which again seems to be very far removed from everyday experience. But the GPS navigation system that we all use every day nowadays only works the way it does because we take into account the effects of general relativity. Otherwise, the planes would all land in the wrong place and we'd never be able to get to Grandma's house.
Sounds very important, and great achievements are made in physics. And you
So
worked...
if I could come to the second half of your question about
Yes.
international collaboration. So it's clear that particle physics, or also many aspects of astrophysics and cosmology, are big science. They require large experimental facilities or large telescopes. They typically involve collaborations of hundreds, maybe even thousands of people. So those facilities, those collaborations are necessarily international. And the internationalization of experiments and observations in fundamental science is something that's been growing over the last 50 years. Now, I've seen it in my own lifetime. When I was a postdoc, it was very out of the ordinary to have a collaboration of 50 people. And I remember a senior physicist telling me, "Oh, that's the upper limit. You can't have collaborations which are larger than a baboon troop." But it turns out you can. And now at the LHC at CERN, for example, the Higgs boson was discovered by collaborations, each of which included something like 5,000 scientists and engineers from over 100 different nationalities. And what brings all those people together is a common objective, and a common objective which doesn't have any political ramifications. It's just understanding the way the universe works. It's, I'd say, the purest of the pure sciences.
And did this change with the invasion of the Ukraine, with the Russian invasion of Ukraine? Did the collaboration change?
So, of course, as you know, many countries in the West, Western Europe, and also North America, announced sanctions against Russia when the invasion happened. And among the CERN member states, there was a lot of discussion to do whether to continue collaborating with Russian physicists or not. And finally, the decision was taken to terminate official cooperation agreements with Russia. There is still one sort of, if you like, chink in this particular armor, which is in Russia, there is this international research institute called JINR in Dubna, and physicists from Dubna can continue to work at CERN. So that's an exception, but otherwise, physicists working for Russian institutes can no longer work at CERN.
I understand. What was your biggest challenge working for CERN?
What was my biggest challenge? Well, I think one of the issues at CERN is obviously it's very, very stimulating to be surrounded by hundreds or thousands of physicists, and there's many opportunities for discussions about physics and other things. So sometimes it's a bit of a challenge to actually focus on one's own research and at least metaphorically close the door and concentrate on one's research projects. I should say that I generally leave my door open. In fact, it's even open at the moment. It's just only very slightly open. But I like people to know that I'm here and that in principle I'm available if they want to talk. But of course, if everybody talked, then I wouldn't be able to get anything done.
Sounds great. And for a social scientist like me, could you explain in a more easy way what is, for example, the Higgs particle, or what is a black hole, or what are you researching on? How can we imagine that? Is this mathematical, theoretical, or how can we understand this?
So I think that both the Higgs boson and the black hole were objects which were postulated by theoretical physicists who sort of followed through the consequences of their equations, and they said, hey, well, look, there should be this thing out there, right? And in fact, the history of black holes goes back probably a couple of centuries, because even before Einstein's theory of general relativity, people were saying, well, look, you just take Newton's gravity, and there's some sort of singularity there. And that's what subsequently became known as a black hole, although the name black hole didn't come into currency until much later. Similarly, with the Higgs boson, people said, well, look, we've got all these particles, many of them have masses. Where do those masses originate? And so Peter Higgs and other theoretical physicists came up with an idea for where those masses might come from. But it wasn't completely obvious how you would actually verify their theory. And Peter Higgs, who made the key observation that, according to his theory, there had to be another particle, which was not discovered. And in fact, it took 48 years from the time when he postulated, just on the basis of mathematical consistency, the existence of this particle. It took 48 years until it was actually discovered experimentally.
Let's talk about also the link between physicists and peace. I did an interview also with Hannes Jung, who worked also for DAISY, and he brought to life the Science for Peace Forum, which is a great place where we can discuss different topics. Hannes also invites every time different people to hold a speech or give a lecture. And it's a great place. So how would you describe the interests of physicists in peace, or let me frame the question in a different manner. How do you see the role of physicists and the peace advocates, for example, how they intersect?
So I think that since we're interested in fundamental science, without regard to applications, I think it's intrinsically a peaceful subject. And in fact, in the Constitution of CERN, the convention says, right at the beginning, that the organization shall not get involved in military research. I would say also that the fact that it brings together people from many different countries, many different cultural systems, political systems, geopolitical blocs, and so on, means that it benefits from and flourishes in a peaceful environment. Also, since it's intrinsically a sort of a politically neutral type of research, I think it provides what you might call a safe space for people from different perspectives to come together and discuss in ways that might not be possible otherwise. And a very interesting example was back in the 1980s, there were disarmament talks taking place in Geneva between the US and the Soviet Union. And they weren't going so great. And then the then Director General of CERN invited negotiators from the two sides to come and visit CERN. So they came and visited CERN, and they sat down for a meal in the restaurant just over there. And apparently they made significant progress in terms of resolving their discussions about nuclear disarmament. So, well, I think that gives you some sort of idea of the positive relationship that exists between fundamental science and peace.
Sounds great. I can also remember the Russell and Einstein manifesto. Bertrand Russell and Albert Einstein wrote a wonderful piece, I believe in 1955, and they warned the world about the dire consequences of nuclear war, the use of nuclear weapons. Can you see a parallel to that time? Aren't we in a similar spot, in a similar dangerous time of nuclear escalation?
So I think we're facing many dangers to civilization at the moment. And I would certainly agree that nuclear escalation is one of them. There are others. There's the possibility of climate breakdown. We know that climate is changing, and we know why it's changing. We know what needs to be done in order to stop that continuing and, if possible, reverse it. But that's a crisis which is still denied by many people, and the sort of strong actions that we need are not taking place. And I think that's actually just one example of a more general issue that civilization faces, which is we live on a planet with obviously limited resources, and we just, in many cases, literally burning them up without thinking about the consequences. And for example, if we want to continue using metals in the way that we use them, we're going to have to recycle them at a rate of 100%. When I say 100%, I don't mean 99.9%. I mean 100%. Otherwise, our existing civilization cannot possibly continue for millennia to come. So, like I said, I certainly agree that nuclear escalation is a severe issue, but there are also others.
Absolutely. And you talked about also the shared experience, and that many scientists from many different countries and nations are working together. One of them, one of these large-scale projects is the Large Hadron Collider, which involved international partnerships. And did you work with that Hadron Collider? What was what is this big machine all about?
Okay, so this is a device that tries to recreate the conditions that occurred very early in the history of the universe. When I'm talking about very early, I'm talking about maybe a millionth of a second after the Big Bang. And what we try to do with the conditions that we recreate in the laboratory is to understand how the universe evolved when it was very, very young. And so that might, for example, have been the time when dark matter emerged from the primordial soup. We certainly believe that was the time when particles started to acquire mass. Previously, they would have had no mass. So those are sort of the fundamental scientific objectives that we're after. Now, in order to do that, we have this ring, which is 27 kilometers in circumference. It's buried on average about 100 meters underground, so you can't see it from the air. And we have large numbers of protons, fundamental particles going around in opposite directions, and at a few places around the ring they collide. And as I said, they recreate what's happening in the very early history of the universe.
something was awkward with the audio, with the sound. I'm sorry. I hope now it's gone.
I don't hear anything strange.
Okay, I will turn off my mic. Maybe then it's better. So, you were talking about the Hadron Collider.
Yeah, and how it recreates what happened very soon after the beginning of the universe, and that enables us to at least think scientifically about very fundamental questions like how did the universe get to the way it is today, where did the matter in the universe come from, what is the dark matter, and so on. All of these, of course, are very fundamental questions and not things that people don't usually worry about in their commute.
So something is very awkward with the sound. I'm so sorry. I'm not sure why is that.
I can't hear you. Perhaps you could write your questions in the chat.
Now maybe it's better. Yes.
Okay, yeah, I can hear you.
So also one of the topics that you are interested in and that you have done research on is the quantum gravity. There are many different terms, and I'm not sure what is the difference between, for example, quantum mechanics, quantum physics, and quantum gravity. Maybe for somebody like me that doesn't have a clue, maybe we can start from here. What is the difference?
Okay, well, if you want to understand atoms, you want to understand why electrons in atoms have the very particular energies that they do, you need to invoke what's called the quantum principle. Those energies are discrete, and as a first approximation, the discrete energies are determined by what we call quantum mechanics. But then if you want to do a more complete calculation, not just of energy levels in atoms, but for example, collisions of particles, what we were just discussing in connection with the Large Hadron Collider, then you need a more complete and more sophisticated quantum theory that describes all different fundamental interactions. So that's what we call quantum field theory. And the particular quantum field theory that describes all the visible matter in the universe is something that we call the Standard Model, which is a rather humble name, but it's actually a very powerful theory. But the Standard Model does not include gravity. And in fact, one of the challenges ever since people started thinking about quantum mechanics and general relativity has been, how do you combine those two? So how do you combine quantum theory with gravity theory? And so that's a puzzle which has been with us now for about 100 years. And at least in my mind, it seems to require a theoretical framework which is more powerful and more general than quantum field theory. So if you like, there's a nested sequence of theories. There's quantum mechanics, there's quantum field theory, and then there's quantum gravity. And physicists have been struggling with quantum gravity for 100 years, and there are, I think, some good ideas about the direction in which one can proceed, but we're not there yet.
Do you have your cell phone nearby? Because I'm hearing such a noise. Maybe it's from that. I heard also that that from the chat that somebody is confirming that there is still an issue with the sound. I'm not sure why, but now I hope it's better. Okay, now it's okay. It's not the cell phone. Maybe it's the internet. I'm not sure. I'm not sure. I'm sorry. But it's recorded anyways. So yeah, hopefully we can upload it if.
Yeah, so maybe clean it up later.
Yes. So and this quantum theories, did they, in your opinion, is Einstein's theory of is it obsolete, or is it based on Einstein, or how? Maybe it's a dumb question, but
Einstein, I think, struggled with quantum physics. So in 1905, he used the quantum principle to explain the photoelectric effect, what happens when you shine light on a metal. And that was actually why he got the Nobel Prize. It wasn't for relativity, it was for his theory of the photoelectric effect. And his theory depended on the idea that light comes in little lumps called quanta. But it didn't really play an active role in the development of quantum mechanics later on. And he's famously quoted as having said that he doesn't believe that God plays dice with the universe. So, and he tried to find paradoxes why, if you think about it carefully, quantum mechanics couldn't possibly be right. But I don't think he convinced people, apart from himself. So anyway, this debate actually at some level is continuing. So the Nobel Prize winner, Gerard 't Hooft, who did some of the really fundamental work proving the standard model was a sensible theory, he doesn't like quantum mechanics. So it's intrinsic to quantum mechanics that there are some things that you just can't predict. And 't Hooft says, well, I don't really think that. I think that actually there is some sort of little, dare I say it, clockwork mechanism operating down there, which behaves in a deterministic way. And to the extent that we don't fully understand that mechanism, so we can't actually understand what its predictions are, we come up with this theory of quantum mechanics. I'm sorry, I'm not with Einstein and 't Hooft on this. I think quantum mechanics is a fascinating, wonderful, extremely powerful theory, and I'll stick with it.
Oh, I'm going back. Okay, now I understand. And let's dig deeper a little bit about all my knowledge about black holes, for example, is that they, how can I explain it? Their gravity is so huge that they absorb even whole planets. Is that correct? And if it's true, where is the end of this process, and where is all this mass going to? I cannot imagine this process.
Yeah, well, black holes can absorb planets, they can absorb stars. So the fundamental issue, which, as I mentioned, actually came up even before general relativity, is that gravity pulls things together. And the closer you pull, the closer the matter comes together, the stronger that pull together becomes. And so in principle, it could be a runaway effect, right? That if you've got a very dense clump of matter, it tries to contract, and it will be able to pull in more and more matter. Now, on Earth, we're familiar with the pull of gravity, right? But we know you can escape it. You can escape it by launching a rocket, which travels at more than 40,000 kilometers per hour. Okay, and then it will escape from the Earth's gravity. If you had a bigger object like Jupiter, then you'd have to go to a higher velocity. And if it was the sun, you have to go even higher velocity. And so the issue is that if you've got a sufficiently large amount of matter in a sufficiently small volume, when you calculate this so-called escape velocity, it becomes equal to the velocity of light. And at that point, since nothing could travel faster than the speed of light, anything close to that object is fated to fall into it. And this is something which people have been worried about, as I said, for a couple of centuries. And in Einstein's theory of general relativity, Einstein's theory of gravity, it's an unavoidable consequence of the theory that there should be solutions to the equations, which what we call black holes.
And also there is a question from the chat. Thomas is asking, so is the gravity at the singularity not normal gravity as we humans experience it?
So there's a question which I think you implicitly at least already asked, which is, what goes on inside a black hole? And the answer is, well, we don't know, because no light, no message can get out. So we have to rely on our equations. But eventually our equations just break down. That's what we call a singularity. And the way things stand at the moment, those equations break down inside every black hole. So there's a lot of discussion at the moment about what happens in the neighborhood of that singularity. But for the moment, I would regard that as being not yet established. And although theoretically it might be well-founded, I'm not sure experimentally how we'd ever be able to test it.
And what about the dark matter or dark energy? How can we imagine that?
So the matter, the visible objects in the universe, like you, me, planets, stars, those are well described by what we call the Standard Model. I can write you an equation on a T-shirt which will describe their behavior. Okay. But it was observed already 90 years ago by the Swiss astrophysicist Fritz Zwicky, that if you look at clusters of galaxies are moving around each other, and they're moving around each other surprisingly fast. In fact, so fast that they would not be held together by the gravitational field generated by the galaxies themselves. So he said, well, there must be some additional source of gravity, but we can't see it. It doesn't shine. And so he called it dark matter. Well, actually, he called it dunkle materia. But anyway, so that was in the 1930s. I think astrophysicists weren't convinced for some decades. But then in the 1970s, observations by the astronomer Vera Rubin and others showed that also inside galaxies themselves, stars move around, quote unquote, too quickly. And again, you have the same problem. What holds them in place? And so the idea of dark matter, invisible matter that exerts a gravitational attraction, eventually reached a consensus amongst astrophysicists. So that's dark matter. It gravitates like regular matter, but it doesn't have electric charge. dark energy is something which was first postulated, in a sense, by Einstein in 1917. He realized that his equations allow for the possibility not only of matter, which is attractive, but also for the possibility that in empty space, where there's no matter, there might be a sort of repulsive gravitational force, something which used to be called the cosmological constant. So this has been a sort of theoretical idea for a long time. And eventually, in the late 1990s, observations seemed to indicate that this cosmological constant was really there. And I think that by now, there's a pretty strong consensus amongst astrophysicists and cosmologists that there is something, pushing galaxies apart, some source of energy in empty space, which is pushing things apart. Now, there is still a discussion as to whether it's constant or not. And so that's why people tend to prefer the name dark energy to the original name of cosmological constant. And there's some observations at the moment that indicate that maybe this energy is not constant, but is in fact gradually decreasing. I have to say I'm not yet convinced, but wait and see.
Okay, I understand. Maybe I don't understand, but I will pretend that I understand. So Thomas asks in the chat, if space itself is a medium and has properties, could we treat space as a fluid, and in a singularity space itself is changing into something else? I'm not sure.
I think Thomas has a very good question there. So, in fact, when we think about empty space, one might naively think, well, there's nothing there. In fact, there are things there. There are particles that flash in and out of existence according to the laws of quantum mechanics. And as we've just heard, there may be some sort of background energy density in empty space. And that's actually a feature already of, for example, the Higgs theory of where particle masses come from. So according to his theory, there is some universal medium which interacts with particles, and the masses of the particles depend on the strength of that interaction. Now, the amount of energy which you could have in the Higgs field is indeterminate. Okay? So what observations seem to be telling us is that there is energy in empty space, which is non-zero, but very small, much smaller than what the Higgs might be able to contribute. So that is kind of a puzzle. Okay, so we have this theory, the Standard Model, which is incredibly successful, which predicts that there should be energy in empty space. Doesn't tell us how big it is, but the amount that seems to be there is way, 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 way smaller than what you might expect on the basis of the Higgs theory. Now, to the extent that empty space is a medium, and to the extent that it is subject, presumably, to the laws of quantum mechanics, you might imagine that when you're in a region where the gravitational field is very, very strong, for example, close to a black hole, that there might be the possibility of some sort of a phase transition where, whereas on a large scale, you get fluctuations. When you go to smaller scales, maybe those fluctuations get bigger and bigger. And when you get to very intense gravitational fields or very, very high energies, maybe those fluctuations get so big that the concept of space-time doesn't make any sense anymore. So I think that's a very interesting idea, which I've myself speculated on in the past. But again, it's the sort of thing that it's very difficult to test experimentally.
As I studied for 2 semesters theology, I'm interested in the beginning. But let's keep God aside. How can we understand the beginning of the universe? Before the Big Bang, how can we understand that there was something? I cannot imagine. Is the beginning something empty, something, yeah? How can we understand the beginning? Because there there must be something out of which something else emerge, or not?
Well, as you say, or not. So the laws of physics, I think, don't allow us to say anything sensible about what happened at time zero, and no, even less about time less than zero. So what happens is that you go to smaller and smaller times after what we think of as the Big Bang. Our laws of physics continue to work, but because of quantum fluctuations in space, which are likely to get bigger and bigger, the closer and closer you get to that singularity, at some point we expect that the laws of physics that we understand will break down. So maybe that some super Einstein will come along and come up with a theory of what happens under those circumstances. But until that happens, we can only discuss what happens at time bigger than zero, but I would say not what happens at time equal to zero, and even less what happens time less than zero. The laws that we have just break down.
Also, maybe a last question, and then I would ask you about some recent developments in the military. But maybe before I go, because it has also to do with quantum physics. But before I go to that question, I'm fascinated by this experiment by Schrödinger's cat. Maybe you can explain what did Schrödinger with his cat discovered. How is it possible that it's a paradox in a sense. How can the cat be alive and dead at the same time?
Right. Well, first thing to make clear is that Schrödinger never did anything to any cats. This is a purely theoretical consideration. And so basically what he said was, well, look, quantum mechanics, if it's the right theory at the microphysical level, then what happens when you consider larger and larger scales, where you get into what we would call macrophysics as opposed to microphysics? And we specifically considered as I said, not a real experiment, but a Duncan experiment, where the cat would be alive or dead, depending on some quantum mechanical process, which, as we discussed earlier, according to quantum mechanics, is intrinsically unpredictable. And so what quantum mechanics would tell you is that in that situation, the dead cat and the alive cat should be a quantum superposition. So the cat would be, in some sense, in the same state, so in different states simultaneously. So I think most people would accept, well, that's kind of a paradoxical, because cats are clearly either alive or dead, right? You can't have something which is a superposition of a live cat and a dead cat. So I think what Schrödinger's cat paradox illustrates is that there is an issue of how the transition takes place between intrinsically unpredictable microscopic quantum world and the apparently predictable large-scale classical description of physics. And I think that issue might have been one of the reasons why Einstein was so keen on the idea that there might actually be some sort of deterministic process taking place even inside an atom. But I think most physicists were not convinced by his arguments, and most people think that there must be some other interpretation of Schrödinger's paradox.
Let me move on. A few days ago, maybe yesterday, I was reading in a newspaper that there was some rather revolution discovery that quantum tech ends this cloaking dominance. So this stealth jets that can hide from detection and radars, now they discovered something that ends this invisibility. Did you have any information about that? Did you heard something about that? What's your opinion on?
I am afraid I have no expertise in this area, and never having had anything to do with military research whatsoever. I mean, I can understand, in a naive way, that you can design a jet plane or a ship so that it could not be detected using traditional detection methods. But there's so many other detection methods that eventually there might be some way of detecting their existence. So what can I say? Well, let me tell you that for sure that's going to be the case. Because if you have a jet plane or a ship, it's a blob of matter and it exerts a gravitational force. And even if you can't see something, you can nevertheless detect the gravitational field that it generates. And so in principle, that would be possible for a stealth jet or a stealth ship, although I think we're a long way away from being able to detect that gravitational field. But in principle, it will never be possible to make something which is completely undetectable.
Very interesting. And you mentioned also in the beginning, I believe we mentioned this, and Hannes Jung is also an advocate for no military use of science and especially at CERN. And there are some recent developments that so the government in many countries, especially in Europe, are trying to some sort of militarize the university or militarize also the knowledge and research. What is, in your opinion, the recent developments and how is, for example, all the member stuff in CERN and DESY and these huge research facilities, how they are reacting to this recent development?
So, as I mentioned earlier on, it states very clearly in the CERN Convention that the laboratory shall have nothing to do with military research. And this is, to my knowledge, applied rigorously. So, for example, I remember some years ago, I was accompanying the then CERN Director General on a visit to an institute in a country that I won't bother to name, and about the possibility of scientific collaboration. And I had a tummy upset, and I had to leave the room for 5 minutes. And when I came back, the atmosphere completely changed. And what had happened was that the Director General had discovered that this institute was also engaged in military research. And he said, no collaboration, impossible. So that's CERN. I think it's as pure as can be, which is probably not 100% pure, but at least I think a very sincere effort is made to stay away from anything which is military research. So I'm aware of the fact that in Germany the situation is more complex. So many universities have a principle that they shall not be engaged in military research, the so-called civil clause. And DESY has also been applying a similar principle. However, the previous Director General of DAISY, but has now been handed over his position to his successor, said that maybe, said last year that maybe DAISY should consider hosting some military research, or at least dual use research. So I know this is a very active debate in Germany, and I have every sympathy with Anders Jung and his colleagues who are deeply unhappy about it. The situation in the UK, I think, is somewhat different. We have military research laboratories, that's for sure. But I have never ever come across anything remotely resembling military research during my time at King's. Not to say that it doesn't happen, but it just doesn't seem to be an issue at the moment.
And now this is a funny question. I have to ask it. Thomas from the chat asks a Star Trek warp drive question. I'm not sure you know Star Trek, this series. Would it or is it possible to detect a ship traveling in such a manner? So with warp, understanding that warp drive is not faster than light, but the warping of space-time.
Well, so since I don't know how to construct a warp drive, and indeed I don't think anybody else knows, we can't say what its gravitational effects might be. I would be, again, somewhat surprised if you could accelerate a spaceship to very close to the velocity of light, and it didn't produce a very strong gravitational effect. And in fact, there is some discussion in the scientific literature about possibly being able to detect ultra-fast spaceships belonging to some super advanced technological civilization. Okay, I think I would prefer to publish my papers on that subject only on April the 1st.
I believe we have no further questions from the chat as far as I can see. Let me see if I asked all my questions. We talked about the Hadron Collider, we talked about Science for Peace, CERN. Yes, this dual use for military purposes, we touched on that. Yeah, it's a difficult interview for me because I don't have a clue about any of your research, so I'm sorry if I if I'm not competent enough to go deeper and to dig deeper and to ask tough questions but it's not my field of research, and I'm fascinating although.
You and some of the colleagues who are on the call come up with some very interesting questions, and I hope that I've convinced you that I don't have all the answers.
Yeah, nice. So I hope it was also in the spirit of this peace talk that we mentioned that, for example, the Einstein-Russell manifest, we mentioned in the 80s that scientists did some effort in diplomacy, and yeah, I hope we held up this spirit in yeah.
Yeah, well, let's hope that in the future somehow this spirit of science for peace can be retained and developed, and the current trends towards cutting scientific collaboration between geopolitical blocs, I hope that that trend will eventually be reversed, because I'm convinced that the most efficient way to make scientific progress is to work together.
Yeah, hopefully we will tackle as humanity the climate crisis, and hopefully we are not on the brink of nuclear war or World War III. Hopefully we are intelligent enough to Yeah, or maybe some aliens are coming and they will teach us how to do it. I'm not sure what is more realistic.
We better be careful about the aliens, right? I don't know whether you've read the Three Body Problem series of books. It's a Chinese science fiction story, which is very cautionary. Three Body Problem.
Oh, never heard of it.
Well, Google Three Body Problem, and then you'll maybe see what I mean.
Okay, but it's interesting. Didn't the Trump administration try to discover something, or did they make many papers public, maybe classified documents about aliens and some
I
stuff?
don't know about aliens. They published classified documents about the assassination of John Kennedy, but I don't think there was anything there.
Yeah, yeah, and even if it would not change that much, I believe. So, yeah, dear Professor John Ellis, I thank you very much for your time and for your knowledge, and also that you are engaging in the Science for Peace Forum. And yeah, I hope we can read in the future many of your articles, and maybe we can witness another discovery. And yeah, thank you very much.
And more peace. Hey, goodbye. Thank you again for